16.2 is about cloning. Um, so cloning is making a new organism without doing meiosis, without fertilizing, essentially taking an adult or at least an existing organism and making a new copy of that organism. Genetically, they're identical to the parent. Um, Phenotypically, as far as what they express, maybe not. But this is going to make a big difference in what we're going to be able to do in the future of medicine based on how these develop with stem cells. And you might think of cloning as a super new thing. Not necessarily. Carrots in the 1950s, taking cells from roots, stem cells from roots essentially, and growing them into adult plants. So that was the first making of a clone. Um, Cells that are young enough are called, or that can become absolutely anything, are totipotent. As a cell changes, it gets a little older, there's fewer and fewer things it can become. But totipotent means it can become absolutely any kind of cell. Um, Animals are harder than plants, or were harder, still are harder than plants to clone. So how exactly is it done? Well, you take an egg and you knock out the nucleus. You take a nucleus from another cell and you stick it in there. Um, a lot of times you have to provide some chemicals to get it to start, certain factors, and it will start developing just like a normal um, zygote. But what's been found is the age of the nucleus that you're using, the donor nucleus, seems to matter. So two guys, Gurdon, um, experimented with eggs. So if you take the egg cell of a frog, and we're going to zap it with UV light to take out the nucleus, essentially. We have an egg with no nucleus that, if we put in a nucleus, will develop. Two ways you can do this. You can take a cell from a tadpole, so not that old, but it's already become a specific type of cell, in this case an intestinal cell. We pull out that nucleus, put it in the egg, and we have now this. And we've used the right factors, the right proteins, etc., to make it start growing. It starts developing, and a lot of times they didn't make it. I think it's like 2% made it. Most of the time they didn't. So that isn't the best. If you were looking at another frog embryo, this is like at the 4-cell stage, if you pull those nuclei out, put them in the egg, that tends to be more successful. So if there's something about the age of the embryo and whether that embryo came from a cell that is more wide open, more totipotent, or has it sort of specialized already, seems to make a difference. 97, the first reported cloning of a mammal. Um, Same deal, take an egg, knock out the nucleus, take a nucleus from another sheep, put it in that egg, give it the right mix of chemicals to make it go, and it develops into a clone, exact copy genetically of that sheep. But sort of the same problem. The cloned animal seemed to age quickly. It came from a cell, I believe it was an udder cell from a sheep. That nucleus had sort of aged, it had already differentiated and it had its path set, and that seems to be a bad thing. So what they've just learned is that you need to trick that nucleus into thinking it's young again. So as a nucleus goes through stages, parts of the DNA are going to become more or less accessible, which is part of cell aging. If you can undo some of that, make it young again, you'll have a lot more success. So there's Dolly. Lots and lots of mammals have been cloned. Probably not humans. Can't guarantee it. CC, the first kitty. But even though they are same genetically, depending on what their environment has been like on them, some genes might get turned on or off differently in different parts. So CC and mommy, and CC's mommy is technically the same, just older, since CC's a clone, which is really weird. The one on the left is Rainbow, the mom. The one on the right is CC. Rainbow's Calico. CC isn't. Interesting. Different X's turned on. So by epigenetic, that means above genes. Basically the things that influences not so much what genes are there, but whether they're going to be turned on or off. So you have to sort of get rid of the traces of time, of what has happened to that particular nucleus, to make it different as it ages. So if we can turn back the clock, we will have a better clone. The reason this is important is if we can figure out how stem cells work, we can essentially repair any type of cell, any type of tissue, any type of organ, which would obviously be huge. No more waiting for a donor organ that may or may not work. If you could grow an organ that was exactly like your original organ, you'd be in very good shape. So we need to understand about stem cells, and there's still a lot to learn. But basically, a stem cell can become anything or almost anything, depending on the type. It can either make more stem cells, or it can become a precursor cell, something that's more specialized. Now, a precursor cell can't become anything. It can become a few things now. It's a little more specialized. So this particular type could become different types of cells: fat cells, blood cells, bone cells, blood cells. Probably not nerves. That'd be a different type of precursor cell. Earlier on in embryonic development, cells can become almost anything. Totipotent is absolutely anything. Pluripotent is almost anything. Almost anything. Could become nerve, bone, hair, skin, what have you. Liver. Those are a lot more wide open. As you age, you have an adult stem cells too, but they're more specialized, like the ones seen previously. A precursor cell would be a type of stem cell that is a little more specialized. It can't become anything. So if you take a stem cell from an embryo, it can become just about anything if you give it the right signals. It can become the types of precursor cells to be liver, the types of precursors to be nerve, the types to be blood, etc. By the time you get adult stem cells, like the cells within bone marrow, they're already sort of set. They are more of a precursor cell that can just be blood cells. You can't early on, you can't make them go to liver or nerve, at least not right away. The tadpole guy and another dude from Kyoto, Japan, received the Nobel Prize for doing that, turning back the clock, taking cells and turning them back to pluripotent. So instead of regular pluripotent from embryos, these are called induced. We're taking adult cells and making them turn back into pluripotent. This is big for a couple reasons. One, using embryos is very controversial. It depends on your opinion. It depends on your ethics. It depends on your morals, on how these should or should not be used. However, if you're taking cells from an adult and you're not hurting the adult and you can make them go and do almost everything that those embryos can do, you don't have to worry about the ethics of the embryo. We can just take them from adults. By the way, gets a prize, Nobel Peace Prize. Who did he work with? The guy up the road, James Thompson, University of Wisconsin, Madison. Did the same thing about the same time, different factors. Why doesn't he get a Nobel Prize? I don't know. He's darn close. So it took a stem cell. I'm sorry, not taking a stem cell. Stem cells become precursors. They become skin. What Yamanaka and Thompson have done. Yamanaka used these 4 genes to turn back the clock. Thompson used 4 different genes, but they're able to take this skin cell and turn it back into a stem cell. They induce it. They make it go to pluripotent. So now, not only would you be able to grow a new, say, organ, it would be from your cells. It would be specific to you. There would be no worrying about organ rejection. They're your cells. And you don't have to worry about the ethics part of embryos. And actually, Dr. Thompson was the first to grow a line of human embryos way back in '98. Way back there.